All right, we are back after a short break with another exciting talk by Justin Ohneiser from Booz Allen Hamilton. He will talk about web cache tunneling today. Welcome.
Thank you. Hi, everyone. My name is Justin Ohneiser. I am a security researcher at Booz Allen Hamilton. I get to talk to you today about web cache tunneling and covert command and control. But first, I'd like to welcome each and every one of you to the new hacking organization, Pseudonymous. I don't know if there's an existing Pseudonymous, and we have no relation if there is. This is definitely a totally not lame group that we're joining. You and I together today will be in charge of network communications in our malware development department. Malware is something we deploy when we get access to a target. It is something we leverage in order to accomplish our objectives. So it's very important that we can communicate with it reliably and covertly. So our responsibilities are to make sure that the malware communication is reliable or the operation could fail. But remember, we're a covert organization. So this communication needs to be undetectable or the operation could get caught. It needs to be untraceable or the infrastructure could get caught, stopping future operations. And it needs to be unattributable or we could get caught and lose our freedom. So what are our options? Well, there's the tried and true TCP stream. We have malware connect directly to our infrastructure over a TCP connection. This is extremely reliable communication. It's going to be fast. However, it's going to be detectable. Defenders are going to be on the lookout for long-standing TCP connections, and they're going to see that this is communicating to our infrastructure, which may be new or suspicious. Once they detect that infrastructure, they could investigate it, potentially revealing our identity. So, what other options do we have? Well, instead of a long-standing TCP stream, maybe we beacon over HTTPS. This is an extremely common protocol, and not just for malware today, communicating using this protocol, but it's likely the most common protocol in the defense that the defender will see in the network. It is no longer a long-standing connection, it's intermittent, it's encrypted, and it's going to blend in extremely well. But again, if the malware gets caught, maybe the host team left a few extra logs on the target. If we still get detected, this is still going directly to our infrastructure, which could be investigated and reveal our identity. Now, I reserve domain fronting because technically that's not going directly to our infrastructure, but remember, we're not a red team that's going to say, all right, you got me. We're a covert organization that needs to avoid getting caught at all costs. So we can assume that if we got caught using domain fronting, that the authorities would then cooperate with the cloud provider that's enabling that technique. So for our purposes, domain fronting is still connecting directly to our infrastructure. So finally, we could do something really creative. We could set up a Twitter profile and have our beacon directly to Twitter's infrastructure instead of our infrastructure, checking for updates to that profile. Now, this will accomplish the same thing, but instead of communicating and revealing our own infrastructure, we're just communicating to Twitter. That means if we get caught, there's nothing for them to look at except Twitter. However, again, as a covert organization, we risk Twitter investigating the creation of that profile, and it's expensive to maintain a persona that would satisfy them. So, wanting to do a good job in our new position at this organization, we start looking for something new. And we start at the basics. An HTTP server works by sending a request to the server, which returns a response. Pretty simple, except a lot of people are doing this. So much so that web servers have implemented several different solutions to manage this extra traffic. One of those solutions is a caching server. So in this case, we have a reverse proxy sitting between the user, Alice, and the server. That reverse proxy has the sole purpose of storing responses in a cache with the expectation that another user, Bob, requesting the same resource will accept that original cache response. basically, we're recycling responses for multiple users. What this gives us is Bob experiences a faster load time on the website, and the application server experiences less load, allowing it to help other users and saving on processing costs. So you can understand why the more popular a website, the more likely and the more willing they'll be to use a solution like this. One key point is that each response is stored in the cache under its cache key. A cache key is a set of components in the request that fully identify that request, such that if Alice were to make a request and Bob were to make a request, they would have to have the same cache key components to deserve the same cached response. So we'll go into this a little more in detail. Consider the following search page. This search page is a delightful little bar in the center, and when you put in a search term, it takes that search term, puts it in the URL, and makes a submission to the server. As you can see, we have example.com, and with a single URL argument, q equals foo. Now, this search page has three specific behaviors that are particularly interesting. One is the responses to this search request are cached, which means if we search for the same thing twice, the second response will come back a lot faster. Second, cached responses reflect the requested URL. So when we send a request for this search and we get a response, it tells us what we searched for, basically. Finally, the cache only cares about the q URL argument. Of course, it only cares about what we searched for. It doesn't care about anything else, and the cache likely ignores it. So if we take a closer look at this, here we have two requests and their corresponding responses from the user Alice to the application server. The first response is for a search of the term foo. As you can see, it misses the cache, goes all the way to the application server, which responds no results for foo. Alice then submits a second request, this time including extra data in the URL argument. However, the cache ignores that extra data and says this request deserves the same response as the first one and returns no results for foo. You'll notice it doesn't quite match what the request included. This is standard caching behavior, but let's take a closer look and rearrange it this way. Let's send the extra data first. Here she sends foo and bar to the server, misses the cache. The server then responds, no results for foo and bar. It includes the extra data. Then Alice sends the request with the search term foo. This time, the response is again from the cache, but something very interesting has happened. That response now contains information that was only present in the first request, not the second one. Now, you may notice this is the premise of web cache poisoning. If that extra data had somehow escaped any URL encoding, that extra data could simply be a script tag that now compromises the next user. But let's say it didn't escape any encoding, or they previously had a web cache poisoning vulnerability and solved it by encoding that reflected content. Is it still useful to us? I would argue yes. If we re-describe that exact same situation, but this time Alice sends the first request, Bob sends the second request, we have Alice effectively storing that extra data, p equals bar, in the cache, and Bob is retrieving that extra data from the cache. Web cache tunneling is the premise of using the web cache as a transport mechanism to send data from Alice to Bob by first storing it in the web cache. So, we have our theory. Does it work? Our goal, remember, we're part of this covert organization and we want to build a way to communicate with our malware. So we need a way to write to the cache and read to the cache in such a way that we can communicate between parties. So, as we just mentioned, writing to the cache involves sending a request for both keyed data and unkeyed data. This stores that unkeyed data in the cache once it's reflected from the server. To read that data, we simply send a request for just the keyed data and hope that the cache delivers us the unkeyed data from the previous request. This is reading and writing. So this is our first introduction to our prototype. On the left, you have our prototype cache cat being configured, and on the right, you have a proxy showing us the traffic between our prototype and the web server. We've configured a website, webcachetunneling.com, that specifically exhibits the vulnerable conditions mentioned earlier, and we're configuring our prototype to use that public website. We instantiate a cache object. That cache object checks to see if there's anything stored under the key nothing and shows that there's no cache. There's nothing stored under that key. Now, we check to see if we can store data under the key test. We do, and then we retrieve that data. There. So that's a pretty basic example of storing data and retrieving data in a public web cache. Can everyone see that demo okay? Looks a little blurry from the side. Okay. All right. Thank you. So we have a simple prototype, but we need a little more. In fact, we need to be able to read and write a lot of data, not just a little data. But we have one problem. When we write to the cache, we can't rewrite to the cache. For example, this isn't a socket that once it's open, we can write and write and write. Once we write something a single time, it's now taken. In fact, the problem's even worse. Reading from that slot in the cache also stomps on the cache. And so just merely checking to see if there's data itself writes data to the cache. So we need a way around this in order to communicate. The solution we come up with is a session. In this case, a session is a set of pseudo-random strings that we use as keys. We iterate over that session, and we deliver chunks of data for each item in the session. We do the same thing for reading, and we read each chunk from each session, which again is pseudo-random set of strings, and we should get the same output. So we revisit our original prototype. We have this prototype set with a few extra players. We have the session object, which creates the pseudo-random strings. We also have a cache reader and a cache writer, which knows how to iterate over those streams and chunk appropriately. Again, we configure our prototype to use our demo website, which is configured improperly, as mentioned before. Our cache object knows how to use that backend as a Python database. And we establish some data we want to read and write. First, we establish a cache writer with a session object seeded with the 1337 seed, and we write our data. Notice the proxy shows several requests. It chunked that data into bits and stored it across the session. And we do the exact same thing with the reader. Which allows us to read back the data in full exactly how we sent it. So we have the ability to read and write arbitrary amounts of data, but we still are not quite there. We want to be able to do that, but not just read and write to ourselves. We want to be able to read and write to others. So we need a way to coordinate between different parties. But there's no really comfortable way to guarantee that one party writes before another. We need a generic way of doing this. So we'll reuse our session object. Session object can be used as a stack, such that each client will iterate over that stack, getting to the top of the stack. You know you're at the top of the stack when you reach a response that did not come from the cache. By doing so, each client will iterate and converge at the top of the stack, giving us a findable but dynamic location to read and write data, which effectively bypasses the limitation we originally had with the cache. The way I like to think about this is if you're riding a wave, a surfer's riding a wave, everyone can point to the top of the wave, but that point is always moving. This will be the key to our success. We now have 2 clients on the left and the proxy on the right. We set up the first client with our test environment. And then we connect this client and synchronize it with the stack. You'll notice it'll start iterating over the session. And we do the same for the second client, which now means we can communicate directly between either client. You'll know this usage is a lot like Netcat, where it's taking standard in, sending it up to the cache, and the other client knows how to reliably fetch that data and present it to standard out. So this is the first time we're effectively tunneling directly over a public web cache. Note that neither party actually owns this web cache. This is merely a website that is likely an extremely popular website that happens to have a certain cache configuration that allows it to temporarily store data for our use. Now, if you'll indulge me, let's take another demo and push this to the limit. We now have 2 clients, one on the left and one on the right. The first client is going to set up that same connection to the web cache, but this time it's going to listen on a UDP port. 1337 in this case. You see it's synchronized. We do the same for the second. Now both are connected and each listening on a local UDP port. Next, we're going to use SOCAT to spin up a lightweight VPN that connects to that UDP port. There, we've set up 1 client and 2. And now we have a VPN connecting those 2, tunneling over the web cache. Finally, we confirm our IP address. We're 100.1 in this case. And proceed to ping 100.2. You'll notice it goes through all the stages before returning. And we're getting about 2.5 seconds of delay. So I don't know if we'll be streaming Netflix over this anytime soon, but this will do quite well for malware. And then we simply turn off all the tunnels. We're back to how we were. So that's pretty cool. This definitely works. We know that for sure. We can go to our management with a working prototype. But what have we built? Well, first off, we're not listening anymore. Now, you're listening, but we're not serving a service for the malware to connect to. In fact, both sides are clients. And that provides interesting opportunities. One, we're no longer exposing infrastructure that we need to maintain, or we need to harden, or that the defender could investigate. In fact, because the operator is no longer listening on a service, but is in fact connecting, we're free to connect over anonymizing protocols like Tor trivially, no longer setting up a hidden service. Any logs that are on the web server could easily be to a Tor exit node. And finally, we're not beaconing to a new strange IP address. We're beaconing to a very public website, a very popular website that a lot of people, maybe even the same network that we're targeting, are also beaconing to. So we inherit that website's existing reputation. Problems with this technique are the cache keeps erasing our data. Now this is a positive when we're covering our tracks, but if we have malware that beacons once a day and the cache erases data after 15 seconds, we're going to have a hard time. But other than that, this should work quite well. So who might see what we're doing? There are 3 main players. The web application server is definitely going to see what we're doing. caching server, if it's in fact different than the application server, might see what we're doing. And the local network has a chance at seeing what we're doing. Now, seeing is very different than recognizing what we're doing. They might all see it, but it's extremely unlikely that they'll recognize this as malicious. The application server is going to see logs something like this. The application server is the best bet at determining whether this is malicious or not, mostly because this server likely knows that this search term is supposed to be a word. And so if we're using pseudo-random strings, it might detect that as abnormal. Also, it might detect that we're using URL arguments that are not used by the server. That's something that they might detect, but again, maybe we change our session configuration to use words. Or maybe there's a different configuration where it's not a search box, it's actually a version number that's reflected. That would take away their ability to recognize this. Also, maybe we're using another URL argument that's also used on the web application server. It just doesn't happen to be used on this page. That would also severely limit their ability to recognize this as malicious. The caching server, if it's in fact different than the application server, doesn't have any of those options. It doesn't know this is a search box. It might think it's a version or a hash and not see anything wrong with what we're sending. Their best bet at detecting this is seeing unusual repeated requests, but again, that's a stretch. And finally, the defender is going to see encrypted TLS traffic. That traffic going to an extremely popular website. And even if they're decrypting that traffic, they're going to see search results that look a lot like normal search results. And so in the amount of data that they're looking at, it's extremely unlikely they'll recognize this as suspicious. So what if our technique breaks? There are several ways our technique could break. Let's remember the core vulnerability is the presence of these three characteristics. First, the responses on this page are cached. Second, the cached responses reflect the requested URL. And third, only the Q URL argument is in the cache key. This provides us the ability to reflect unkeyed arguments in the cache, providing the storage mechanism. If the web application server decides to stop reflecting that requested URL, our technique immediately breaks. Also, if the caching server decides to stop caching that page, or all URL arguments are included in the cache key, our technique also breaks. But remember, these are not global solutions, because our situation could have easily been the referrer header is what's reflected, and the referrer is not in the cache key. Because of course, why would the referrer be in the cache key? So this is just another example of how this configuration could have happened, allowing us to tunnel data over it. Generally, if a page is cached, those responses reflect something, and that something is not in the cache key, then it allows us to tunnel data over it. So, pretty happy with our result. We go to management and tell them we found a brand new technique. It bypasses defenses easily. Domain filtering and even deep packet inspection don't even come close to detecting this. Even if our malware does get caught, it completely evades investigation. There's no address, no domain, no server to interrogate. Cache expires content automatically, cleaning our tracks from public view. And even if authorities get involved, forensic evidence is not only split between multiple systems or even multiple companies, but the evidence left there is likely coming from a Tor exit node, and that's all. So you can tell at the expense of a bit of reliability, this technique is severely more covert and dangerous. So they're happy with our result, and then they immediately fire us. So I've left the links here for our formal research on our website. There's also the source code for our prototype, and that prototype knows how to talk to the third link, which is our demo website, which is vulnerable to the specific conditions we discussed today. And my contact information is up here. I encourage you to reach out if you have any further questions or concerns. And if you have any immediate questions, I'd be happy to answer them. Thank you for your time.
Well, thank you very much for this great demonstration. Are there any questions?
Which proxies are vulnerable against this tunneling attack?
Which proxies, you said?
Yes, which caching? Are all caching proxies vulnerable? And if you use SSL interception, is this also possible, this attack?
The first answer would be it's completely proxy agnostic. It has no dependency on which proxy. All proxies would be vulnerable because it's specifically using the core functionality of, caching. It's cache agnostic. So every cache is vulnerable to this because it's the core functionality of a cache, not necessarily exploiting a cache. The vulnerability itself is a mixture of configuration issues, not each cache itself. And you said if something's proxying traffic, can this still be used?
With SSL interception, it might be also possible.
You're saying it might not be possible with TLS interception? Or TLS?
Or is it, I think it's possible, or is it not possible with SSL interception enabled?
I think if there aren't any other caching mechanisms, I think any sort of man in the middle is going to be transparent, but maybe I'm not considering what you're thinking of.
I think about browser-to-browser communication about these covered channels. You have written this in Python.
Yes.
And I think about a different approach. You have a separated network, and they can communicate over the web proxy, and you have a DMZ where you have a client which is able to connect to the internet over the web proxy. And I think you can about a
I see what you're saying.
connection from the air-gapped network, or not really air-gapped, but
Through the DMZ.
from a separate network over the DMZ to the internet, only using a browser as additional gateway.
I'm still not seeing a reason why this would fail, because the same response is coming back, and all we need is that content present in the response, even if it's going through a proxy, and that proxy is going through a DMZ. The response, unless it's stopped somewhere, is not rewritten in any significant way that would break this.
Okay.
I think, unless I'm not considering what you're mentioning.
Yes.
Thank you. More questions?
Thank you. Very, very nice research and proof of concept. Did a field research out on the internet what websites are affected, like Alexa Top 1000 or something like this, or is it on your to-do list?
I've been advised not to discuss what websites might be vulnerable to this technique.
But you did some research about this, like.
Right. I'm a curious guy.
Thanks.
Yep.
Thank you. More questions? We have still a lot of time left. One more question, okay.
Do you think this will stay a possible communication channel for a long time, or do you think this sort of configuration problem will tend to be avoided by bigger companies in the future?
I think it's unfortunately unlikely that websites will eliminate this possibility. The reason I think that is because it's already difficult to approach a website and convince them to change their website based on a vulnerability that directly affects them, let alone one that directly affects their customers. this is a vulnerability that not only doesn't affect the website, it doesn't affect their customers. It just affects some defender that's completely unrelated. Given the difficulty of moving them on direct vulnerabilities, I think it's very unlikely that someone who has this configuration is going to change without any more significant motivation. That's why I think, while this might not be extremely common, I think it's unlikely that those who are vulnerable to this will fix it. I also think that this type of research will become more and more common as network defenders and those willing to sell products to network defenders find better and better ways to categorize their own traffic, that malicious actors might already be using this and might already be using techniques similar to this, which find ways to store data temporarily on the internet and facilitate communication between parties. I think this is a new era of covert communication. I don't think it's going anywhere.
Thank you. We have another question. Oh, okay. Misunderstanding.
So one more question. Did you talk to caching vendors for caching software? And if yes, how did they respond for it? I mean, they could change the default settings. That isn't the problem then.
Right, it's not the cache. There's nothing that the caching vendors can do. It's really
they could change the default settings that there is a unique key and they don't ignore only the second key.
Yeah, and that's the responsibility of the website. And the website a lot of websites avoid, the vast majority of websites do avoid this by doing what caching vendors do recommend, which is on pages that are reflecting content, make sure that the cache status is something like dynamic instead of cached. And so it's their explicit guidance to avoid caching pages that reflect content. That's generally a recommendation from caching suppliers to avoid web cache poisoning. So really this is web cache poisoning as a transport, but it's up to the websites to determine that.
Thanks.
Mm-hmm.
Thank you. One more question.
Do you have any suggestions for the defenders how they can react to this technique?
It's hard. The best I've been able to come up with is malware generally takes some sort of time pattern that could be recognized. Now, putting jitter in here is going to take that ability to detect a routine beacon away. I think the only hope for defenders is for research like this to come out and convince the websites who are enabling this to become public. Even if the websites themselves don't fix the problem, knowing which websites do have this vulnerability would let defenders take a closer look at that website. So instead of it being an extremely popular website we can disregard as automatically safe, we now know it's on a list of ones that could be used for this technique, and so it'll put that back in the box where we take a closer look at it. Other than that, it's nearly impossible to find this.
Okay, one last question.
At the end of the day, you want to send data over this tunnel, mostly to execute some commands. Did you try to do this on a computer, like a real session? I said I want to send 10, 15 commands, then I log off. And how many HTTP requests at the end of the day will be sent out from my network as a company when somebody do this for, I say, 15 minutes? Do I have 1,000, 10,000, more?
Yeah. I didn't do that exact experiment, but what I know about that question is that you may have noticed with that final, actually both of the final demos, the more clients we attached, the faster the convergence process had to happen because it's proportional. The rate at which new pages are cached is proportional to the number of clients connected. If there's 2 clients connected, then what else? Sorry?
So do they cache all the same time, or if there like more clients accessing, they will cache it for a longer time?
Oh, it's completely based on the website. So I have seen ones that cache things for 15 seconds. I've seen things that cache for 2 hours. I haven't done the experiment on how many requests come out, but again, our prototype is just to prove that this works. As I mentioned earlier, you could add jitter to this. You could also change the duration. And so a website that doesn't cache for 15 seconds, caches for 2 hours. Remember, this is a UDP session going through, not a TCP session. And so you could easily have a situation where things beacon a lot slower. And you could, depending on the website that's vulnerable to this, the size of the chunk you need could vary widely. So again, one website that had 15 seconds, I could fit it in the URL bar. But another website that stores things for 2 hours, I could only fit a tiny bit in the refer header. And so it really depends not only on the length of the cache, but the size of the payload you can use.
Great, okay. So thank you for this great presentation.
Thank you.
Thank you.